Bon, je vais le faire en anglais peut-être pour que tout le monde comprenne. So, hello, I have the pleasure to introduce Mathieu Betermin, who will give this seminar today. So Mathieu defended his PhD in 2011 with Hervé Doll at IAS, and he then moved to Saclay for a postdoc with Emmanuel Idadi. And we had the opportunity at the time to work together on an empirical model of mid-infrared to radio galaxy counts based on Herschel observations. So this model is still used today, but Mathieu then went to ESO-Garching, where he worked with Carlos de Bruck on the redshift distribution of submillimeter galaxies, and he also developed many collaborations in France and abroad to observe and interpret many aspects of infrared galaxies at large redshifts. And then he was hired as an astronome adjoint at LAM in Marseille in 2017, where he became the local co-PI, along with Olivier Lefebvre, of the project ALMA Alpine C2 survey. So you probably have heard of that survey already because of the many recent papers and press releases. But so shortly, this survey is aimed at measuring and modeling C+ and far infrared continuum emission in distant normal star-forming dusty galaxies. And so, yeah, we are very pleased to listen to you for more details now, Mathieu.
Thank you, Damien, and also thank you for a long time ago to put my first help me in my first step in modeling, because that was with you. We discussed at IAP, and initially I was a pure observer, and I started also to do modeling. So thank you for that. It was a long time ago, and it was really cool. And I see on the Zoom all the people like I would like to see in real. But thank you for connecting, and let's meet in the future. Let's hope it's a nearby future. So today I will speak about dusty galaxies and their gas reservoir in the high redshift universe. So high redshift would be typically redshift 4 to 6 for the case of Alpine, and I will focus almost all the talk on Alpine. I just put 2 or 3 slides of other results about Lens galaxy in the end. So this result is of course not only my work, but it's the work of many people in the Alpine collaboration. And I would like to dedicate this talk to the memory of Olivier, since basically he was PI of Alpine and sadly left us while the project was close from completion. So it was a kind of a sad event. No, it's okay. So just to start with something very basic. So when we try to understand galaxy evolution, in fact, what we want to understand is how we go from the almost homogeneous universe at the time of recombination that was now very well be characterized by Planck to nowadays universe with all these galaxies, this extreme contrast of densities, this diversity that we see nowadays. And we want to understand the process. So to understand this process, we have now a model which is kind of favored by the observation, especially on the large scale, which is basically the lambda CDM model. And there are all these beautiful simulations, and IAP is indeed involved a lot of them, which show basically how dark matter structures evolve and how basically you form this dark matter halos. But on the other hand, it's still not that easy to explain what happened inside these dark matter halos, and especially the physics of the baryons. And typically, we have to understand many things. The first thing we have to understand is basically how the baryons fall into the potential well of the dark matter halo, how they form cold gas reservoir, typically what's the dynamic of how they fall, but also the problem of how they cool down. Then how they cool down sufficiently to basically form stars. And after the stars themselves, they will have feedback on this gas when they explode as supernova, or even when they radiate UV photons. And you have also the impact of AGN. So all of this can create air flow or also play on the ISM properties of the gas, changing potentially the way that they form stars. So galaxies are extremely complex systems, and if you want to understand them, we need both theory, but we also need the input from observation to basically have access to the detailed physics of what's happening inside the object. And in particular, today I will focus on high redshift galaxies, which are galaxies which are formed early and which have some specificity compared to what we see in the nearby universe. And there are many big questions that are still not fully answered yet, and that we want basically to answer through observation, but also with the help of modeling, which is basically how many stars are formed at early times, basically how early the process of star formation starts, and basically at which space, which is an extremely important constraint for basically the model of evolution of galaxy. And also, how do the star formation properties vary between galaxies of the same type? Because we see that there is some diversity in the nearby universe. So also how homogeneous are these populations, and basically is there some complicated event which basically makes their story very stochastic, or is it a rather smooth history? Also, another key question, especially when you observe very high redshift galaxies, is to basically have access to their gas reservoir, because the gas reservoir, or the baryon reservoirs, which is then used to form stars, is one of the key features to explain basically the transition from basically an accreted blob of gas towards what we are nowadays galaxies. And it's also a very important constraint to the model, because we also want to measure how efficient or quick, depending on what metric you consider, is the conversion of gas into stars. Actually, that's the question of the star formation efficiency in the high redshift universe. Another question, which is a bit more observational, is how dusty are these early galaxies. We see dust now rather early in the universe, and dust is both a problem and also an opportunity. First, it's a problem because it tends to absorb the emission of the UV light from young stars, making it hard to estimate the star formation rate in high redshift galaxies. But it's also an opportunity because it's indirectly a way to prove that there are already metals in these systems very early in the universe. So we have to basically deal with it, but it also can be potentially, when we'll have well understand the dust formation, can be an opportunity to learn more about these systems and the physics in the high redshift universe. Also, another big question is about what the feedback mechanism regulating the star formation in the high redshift galaxy. So I will spoil a bit, but we know that there is a lot of gas in this system, and they could form tons of stars. And at some point, we know that they ultimately stop rather early to form stars for the most massive of them. So we need to understand what prevents this galaxy to form too many stars, and typically the famous problem of outflows, which has been well characterized, I would say, in the nearby universe. It's still hard to know what happened in the high redshift universe when you have much more gas, lots of dense gas. Is it as efficient? Is it less efficient, more efficient? That's something which is not totally clear yet. And last question is about what's the morphology and the deep dynamics of this system. So there's been a lot of debate among observers about what's the contribution of mergers to the very strong star formation versus gas accretion and all these things. And one of the key stuff to look at is basically what's the morphology of the dynamics of the system, to try to see if they are more rotating, merging, clumpy disk. Typically to give input to modelers to try to see if the morphology produced by the model is correct. And basically we can define one or several paths to form nowadays galaxies. So summary of my talk, I will start to introduce the Alpine sample, which would be basically the main focus of my talk, which is basically an ALMA-Large program which aims to study this high redshift galaxy, both the obscure star formation hidden by dust, and also to do some analysis on the dynamics of the gas using the C2 line. Then I will discuss obscure star formation in the redshift interval studied by Alpine. Then after, I will discuss briefly what we learned about the C2 emission of IZ galaxies. And finally, I will discuss the problem of gas dynamics, outflows, and C2 halos, which are a bit less my specialty. So I hope I will be sufficiently clear. So let's start by Alpine. So the Alpine survey is a sample of 118 normal star-forming galaxies between redshift 4.4 and 5.9, and they were selected through optical spectroscopy, typically VUDS and Deimos Cosmos. So they are not all Lyman breaks. Some are identified through the continuous spectroscopy, Lyman alpha emitter, so it's kind of heterogeneous. And there was an attempt to try to select not too biased sample, and also have a sort of UV magnitude selection to have something we can after reverse engineer in terms of selection. So the goal is not to look at the most extreme object like the submillimeter galaxies, which are super star forming, but are also a bit exceptional, and to look at more normal systems, which are close from the knee of the stellar mass function at that time. So typically on the plot on the left, you can see where they are in terms of stellar mass in the x-axis and star formation rate in the y-axis. So you have basically the object between roughly 10 to the 9 and 10 to the 11 solar masses of stellar mass, and a star formation between typically a bit less than 10 solar masses per year up to roughly 300 for the most star forming. So these objects are what we call the main sequence of star-forming galaxies, which is the correlation with star formation rate on stellar mass. The normalization of this correlation evolved with time, but at that time we were right on this correlation. So we are not looking at this extreme system, which are temporarly much more star-forming than the rest of the sample. They are kind of normalish system. But also keep in mind we are at redshift 4 point something or even 5 point something. So an object which is already at a stellar mass of 10 to the 10 is the progenitor of something that will be really massive and much more massive than the Milky Way. So we are not looking at random Milky Way progenitor, but at progenitor of something that we expect to be more massive in the future. So what we target was specifically the C2 line at 158 micron, which is a very bright line, and essentially because it's the easiest to do. And since we have very few spectroscopy at this redshift for sort of systems, that was the first thing to start. And also, since ALMA can observe the line, but also very well the continuum around it, we got for free also the continuum at 158 micron, which is also very interesting, valuable scientific information. In total, it's 70 hours of ALMA time, so it's really a lot of ALMA time in the most compact configuration, because our goal is just to measure integrated properties and not the detail of the system. So there are 3 papers which describe the survey. The first about the goal from Olivier. Then I wrote a paper about the ALMA observation, data reduction catalogs, and there is a paper describing the ancillary data. These 3 papers are basically the reference for the Alpine sample, which basically describes then from which products we did after the science paper. And that's the one we discussed at the coffee with Pierre about writing way too long papers that people cannot really read. So that's a list of the Alpine collaborators. So there were several PI and co-PI across the world, basically people from various collaborations who shared their good candidate of high redshift sources which are good candidates for ALMA targets, and made this sort of project which allied 2 competing groups, which was a great thing to have. Then there are tons of co-Is. And we had also some students who joined the project at the very last minute and really helped us with the data reduction. And without them, would have never managed to do all the data reduction on time before the data become public. So that's also great of them that helped us so fast and so efficiently. Now let's start by what we have done with Alpine. So the first scientific goal for Alpine was to have a first statistical sample for the C2 158 micron line. So why did we target this line? So first, this is a fine structure line of ionized carbon, and this fine structure line is a 2-level system, so it's rather simple in terms of excitation mechanism and things like that. So basically, it's not as CO, which has a complex excitation ladder, so it's a bit easier to interpret. Another thing, it's a bright emission line. It represents between 0.1 and 0.3% of the total far infrared luminosity. So all the emission of dust and cold gas, it's a significant fraction of the total volumetric emission. It's clearly, you can see on the plot on the right, one of the brightest line you can see in this object. So it's also why we went for that, because it's easy to observe. A peculiarity of C2 is that it's originates from both the PDR, for the external layer of PDR, because the ionization potential of carbon is lower than hydrogen. So even in the atomic medium, you have also ionized carbon. So that means with C2, you probe both the photodissociation region, so the place where the gas is a bit denser, and the diffuse H2 region, which is great to have a sort of rough probe of basically the total gas of a galaxy. We'll discuss that a bit later. And also, contrary to some other lines, it's virtually extinction free, so you don't have too much problem with extinction. So contrary to CO, which has huge debate on conversion factor, we don't have too much this problem in this case. And finally, why is C2 so interesting for high redshift science? It's because 158 micron cannot be observed from the ground. But on the other hand, when you go above redshift 4, it enters in the submillimeter window, which can be observed from the ground by ALMA, and then suddenly it becomes really interesting. So that's also why, for high redshift science, it's a particularly interesting line. So in total, we detected 75 detections. So we could cut at 3.5 sigma after making simulation to reach 95% purity, because we are not looking basically at sources in a giant cube, but we are targeting objects. So it's very unlikely to get a feature randomly at this spot. So simulation showed us we could go down to this kind of low cut. And you can see on the right, basically some of the nice detection and also their integrated map. In addition to that, Frederica Loyacono ran a code of blind detection to check if we could serendipitously detect some neighbors, and found 12 additional sources which are related or not to alpine sources, and which are also interesting to constrain many things about neighboring sources. So in total, we got this very nice collection of IZ-C2 emitters. So that starts to be a significant number for Redshift, knowing that C2 detection before ALMA were a couple of quasars, maybe a couple of extreme galaxies, but that was really not a lot of them. And now we can do this on non-lens galaxy in almost industrial way. And that was basically the picture of the Alpine press release that we decided to do to sort of highlight a bit what I've done with the collaboration. So the second thing that we probed is the far infrared continuum, which is basically the emission of the dust continuum, which is around the C2 line and which I can extract with the same exact ALMA data. So why is it interesting? In fact, when you want to probe star formation at high redshift, you would like to make H-alpha spectroscopy, but before JWST, that's kind of a dream. So what you can do usually is to look at the UV light from young massive stars. But the problem is if you have dust, so here in black, the intrinsic spectra of a galaxy, if you have dust, the more the attenuation is strong and the less you will have UV escaping. So you can see, of course, it will change the slope, and you can use this change of the slope to try to guess the correction. But when the correction is more than an order of magnitude, any little mistake on this correction will be dramatic to infer the total intrinsic UV and then the star formation rate. So another way is to look at the UV which escapes the galaxy and combine it basically with the emission of dust, which is basically reprocessing this UV light. So basically you make UV plus IR. So here is this formula, and I will use it a lot in the talk. Star formation rate is basically the star formation rate in IR and the star formation rate in UV. And when I say UV, it's UV not corrected from dust attenuation. And it's linked to the infrared luminosity and the UV luminosity. So for this dusty system, it's essential. And the question is basically at which redshift we can stop to assume there is dust. And the answer by Alpine was like, yeah, it can go pretty high if you look at massive systems. And those adding far infrared data will allow us to measure more accurately the star formation rate. And also, technically, if you detect this dust, that also means it already exists. So it gives some constraints for modelers about the buildup of dust in high redshift galaxies. And Alpine has shown that there is some dust already rather early. So we detected this dust continuum a bit less often than C2. So we knew that to detect for the full sample, it would be a sort of 300-hour ALMA program. So it would have been unrealistic. So we detect only the most dusty system. And for the rest, we'll use a technique which is called stacking to get some statistical constraint. So we have 24 detection. And for the rest, we have non-detection, but you can use stacking. And also for the continuum, we had lots of neighbor of our alpine sources, and we detected 52 additional serendipitous detection around alpine sources, which can be done to study basically dusty galaxy from redshift 0 to typically redshift 6 or 7, but which are not connected physically to the alpine targets. And in addition to that, Alpine is not only C2 and continuum. Why we could make so many analyses on paper, it's also because we had amazing ancillary data in both the Good South and the Cosmos field. So there is spectroscopy from both Keck and VLT, there is HST, there is Spitzer. So there is lots of information about the optical tracer, which basically allow to compare optical property with ALMA. And that's really the combination of both, very nicely summarized in this plot of Andreas face, that we can really say so many things about these systems. So now let's discuss obscure star formation at redshift 4 to 6. So between redshift 1 and 3, we know that obscure star formation completely dominates the budget of star formation. So here you can see it in this plot where you have the redshift, and here you have the star formation rate density. So that's the non-corrected UV, and that's the IR star formation. So you can see between 1 and 3, it's almost an order of magnitude of difference, roughly a factor of 5 only at redshift 3. So at the maximum of star formation in the universe, most of the star formation is in fact hidden by dust. Above, I put a question mark. Technically, there are data points, but there are lots of disagreement between authors, so it's still kind of debated. And that was in 2017, so now we have better constraints, but that's typically what we wanted to consolidate with Alpine. And one of the big questions, kind of naive questions, is like, okay, but when do these two curves cross? Because we know that ultimately you don't have dust, so there should be star formation dust-free at ultra high redshift. But when does dust start to be important? And that was a question we were hoping to answer with Alpine, expecting that the crossing would be around this region. So to do that, you have to deal with some technical problem. And one of the first one is to estimate properly the infrared luminosity. Because technically, we measure only the dust emission at 158 micron here. But to compute the star formation rate, you need to estimate the total bolometric energy of the dust from the polycyclic aromatic hydrocarbon feature here to the basically cold dust emission. And if you change the dust temperature for given 158 micron flux, you will have a very different infrared luminosity. And the effect can be kind of strong, can be a factor of 3 if you take a reasonable range of temperature. So there was some attempt to characterize basically the dust temperature increase with redshift. So here it's a nice plot recently made by Richard Bowens. Basically combines stacking by Herschel by Corentin and myself in blue and green. And then when you go above, there is a couple of attempts using ALMA, using the very high frequency observation. And also the little green square here is what we did with Alpine. And you can see that there is a rise of temperature, which have, of course, an impact on this conversion factor. So in practice for Alpine, in the end, we came back to Herschel. We just stacked sources which were kind of analogous to Alpine in terms of optical properties, and we measured their average spectral energy distribution and found out that we could use the SED I used in an empirical model, and that the Corentin's Schreiber one were also rather good. So basically, we had a sort of average conversion factor to use with a set of uncertainty. And there is a very nice discussion in this paper of Yana Kuzanova about how to infer the uncertainty coming from the fact that you observe one single wavelength. So when you have done all this work, then you can start to measure infrared luminosities of objects, which is directly linked then to the infrared luminosity function, which tell you what the distribution of infrared luminosity of galaxies, which is directly linked to the distribution in the volume of universe of infrared star formation. So to do that, basically we took the serendipitous detection of Alpine at 850 microns. So it's offered basically for free a deep survey at this frequency, which has not been done because most of survey has been done at slightly longer wavelengths because it's slightly more efficient. So that was the first sort of free sample to do that. And it allowed basically to measure this distribution from redshift 0.5 up to redshift 6. So for 4.5 to 6, there is one last tricky step is we should not count the physically connected neighbor of Alpine sources because there is clustering. So there is big work to identify which one are linked to Alpine object and which one are not. But below, normally there is no problem because the sources that we detect at lower redshift are not physically connected to the Alpine one. So it should be a volume of universe which is pretty independent from Alpine. And thanks to that, basically, we managed to push constraints. So here the diamond are Herschel constraint, and you can see with Alpine, we can go much deeper in terms of luminosity and put some constraint on the fainted slope of the infrared luminosity, which was not possible before, and which allow to basically refine our estimate of the star formation rate density at this very high redshift. And the integral of this function is basically the infrared star formation rate density. So basically, how much star formation in the infrared do you have in a given comoving of universe? So that's the first technique for which we can estimate the obscure star formation rate. And then we used another technique which is a bit more indirect and go through a proxy, but for which we don't use the serendipitous detection, but the Alpine target themselves. So the idea is to start from this main sequence of star-forming galaxy, which is in fact the correlation between the stellar mass and the star formation rate. And we know that the Alpine galaxies are on this main sequence. And then basically we use stacking to measure for every bin of stellar mass what the average alpine continuum flux. Then we convert into LIR and we sum with their UV luminosity. And from that, we can get basically the relation between star formation rate and stellar mass. So there are lots of subtleties coming to discuss from the original selection of alpine, which is discussed in detail in Jana's paper. But I invite you to read the paper because it would be a very long discussion, or ask a question if you have. But the main answer is basically that the stack point, which are the square, basically follows the relation which has been previously estimated using optical or over Herschel stacking as this redshift. So basically we kind of constrain rather well this relation now. So when you have done that, you can then consider, okay, you know what the average flux and the average infrared luminosity of a galaxy, depending on proxy, which can be stellar mass, but we also did it with the UV luminosity. So then through big survey for which you don't follow up all objects with ALMA, you can know the number density of this object, so basically the stellar mass function distribution or the UV luminosity function. And so you know the density, you know the average flux, so you just have to combine these two things to get basically an assessment of the total star formation rate density based on what you can measure with alpine on the top and when you can know previously from stellar mass function and UV mass function in the bottom. And then you have to take into account many systematics, the fact that O4 don't agree sometimes on even this luminosity function. But if you take all of that, you can draw kind of large systematic uncertainty, but you can have an assessment of the total infrared star formation rate density budget at a given time. So that's what Jana did. So she found basically the results here in red using two different proxies, stellar mass or UV luminosity function. And then in blue, you have the data for basically UV star formation, and all in orange and red is obscure star formation. So you can see the data are compatible at 1 sigma at redshift 5.5 with the UV, but it's still marginally above. So that means we are probably not fully yet at the crossing between the two. So we are in the regime where the balance between UV and IR is probably changing towards a more UV dominated star formation. So you can also look at the points measured by the infrared luminosity function, which are here, and agree at 1 sigma with the estimates from the alpine luminosity function. So now it seems the story is kind of better understood, that we still have a high IR star formation rate, doesn't decrease really fast, but slowly when we approach redshift 6, we start to get closer from the UV, so we'll soon be in a regime of half-half. Then you can use corrected UV. So there are many techniques to correct UV for attenuation. And you can see that the two scenarios in blue and in red tells roughly the same thing, but infrared is still marginally higher. So we have still to understand that exactly, but there might be something to deal with, but it's a 1 sigma trend. So only the future and bigger sample will tell us the thing. We can also compare with gamma ray bursts, like the Chrysler point, which seems to be a bit marginally higher, but still compatible at 1 sigma. There's still a lot of work to do to really refine that, but at least it gives first indications that even at redshift 6, obscure star formation and dust is really not negligible if you want to measure star formation rate. So after things become a bit more tricky and interesting, if you look not only at the total budget of star formation, but basically properties of individual systems. So here you have a famous plot for observers, which is the link between the UV slope, so the slope of the UV continuum, and the dust attenuation, which is the ratio between the infrared luminosity versus UV luminosity, which is called IRX for infrared excess. And typically in the local universe, lots of dusty systems are following the mirror relation, but here the square are basically the stacks of alpine sources, and they are more compatible with SMC attenuation law, which is kind of what is used now for high redshift systems. But one thing which is kind of scary is there are alpine objects here, 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 here. That means more than order of magnitude above this relation. That means using the UV slope, you may miss an object which have 1.5 more order of 1.5 order of magnitude more obscure star formations than UV star formation, and you could have no clue about it through this UV slope. So that means overall, we have a rough correction, but there can be nasty systems which are completely missed by this technique. On the left, you can see another plot which shows basically the obscure star formation fraction as a function of stellar mass. And especially at redshift 4.5, one striking result is when you go in the low mass bin, the obscured fraction is rather low. It's clearly at 1 sigma below 0.5. But when you go to the high stellar mass bin, you're compatible with something like 2/3 of the star formation being still obscured in this massive system. So that means galaxies which are already massive at this epoch, in fact, have already a lot of dust. And that means basically, okay, dust is important, but it's especially important if you want to look at the most massive system and understand the channels of formation of the most and first massive galaxies, which are expected to be ultimately probably the most massive galaxies in the universe. So all these big elliptical galaxies you can see already at redshift 2. If you want to understand them, you need to have the infrared data to properly understand the in situ star formation very early at the time typically of Alpine, and maybe even potentially slightly earlier. So now let's discuss the C2 emission of IZ galaxies. So one of the big debates that there was before Alpine is, will C2 be still bright in high redshift systems? So there was lots of debate through modeling and things like that. So initially, the first object which has been targeted was very strong Lyman alpha emitter, which has rather metal poor, and people didn't detect C2 very well. So there were a first problem which was coming from the observation mode. They observe at too high resolution. So with an interferometer, you tend to spread the flux across several beams. And if you don't use the correct method and you use beam tapering and some very technical stuff, you may basically think you didn't detect the object, but in fact, just the object is extended. But there are also more physical problems, which are linked to the fact that if you go to too low metallicity, you don't have that many carbon. You have also less dust. So you tend to have very hard and intense UV radiation field from the young, freshly formed stars. And the C2 emission is rather low compared to the star formation rate. While in the local universe, you have this yellow relation between the star formation rate and the C2 emission from Deleuze et al. Here in yellow, which show basically a rather nice correlation with almost a slope of 1. So what's happened in high redshift system? So Alpine was the first big statistical sample to try to really understand what's happening. And in fact, if you take the continuum detection, you can estimate super well the star formation rate, and you have also C2 detection. So that's the system in black. You're very well compatible with the relation, except a couple of outliers. In red, you can't estimate the full star formation with continuum emission, but we use this IRX beta correction to place them. They're also compatible. And in the blue, we made a stacking of the continuum for given beams in mass and redshift to basically check the average position of SFR as a function of their mean C2 that we can measure. And we found that they're under relation. So currently, we have absolutely no evidence between redshift 4 and 6 of a deviation of this relation, which is kind of surprising because we could have expected a slight deficit, for instance, from the prediction from Lagash et al. But currently, we don't see a deficit. That's probably because these galaxies are already sufficient amount of metals to basically behave in terms of C2 physics, roughly like the nearby system. And that's a bit disappointing because we expected to see something new and a bit surprising. But in fact, seeing exactly the local relation is in fact a surprise, and it's not that easy to explain. And another thing, it's a really good news for intensity mapping with C2, which is a future project to map large-scale structure in this redshift range with C2 with other types of instruments, because if it's bright, that means it will be easier. And typically the Concerto project in Marseille, for us, it's really cool because we know that the signal is brighter than we forecasted initially, so that will make it easier to detect. So the conclusion is C2 can be used as a rough tracer of SFR, but we have to be careful because the scatter is really big. It's 0.3 dex, so you can have an idea of it. So it can tell you if your UV estimate of the star formation is completely off, but it won't be a precision measurement of the star formation rate. Another thing we can attempt, which is a bit dangerous, but it has to be discussed with caveats, is we can attempt with C2 to try to have a guess of the gas reservoir in the IZ galaxy. So typically, how do we estimate the cold gas reservoir in an IZ galaxy? So you can use semi-thermal lines. Typically, people use a lot CO, which is basically the most common molecule to do that, but it has an uncertain conversion factor. And also, usually you can't observe fundamental transition, so you have also to assume things about excitation. But that proposition to use other tracer like the C1 line, so the atomic carbon, or the C2 line, the famous C2 line by Papadopoulos and Zanella. So of course, it's not as good as a local tracer we could use, but it could be used as a proxy when we have access to no other information. Then you can use the dust content, assuming that you can have a guess of the gas to dust ratio, which is usually metallicity dependent. And finally, a bit the cool stuff is if you can get it through the dynamical mass, you get the stellar mass. You assume dark matter is on kind of large scale, so at the core of galaxy is not too much a problem. So by subtracting the stellar mass to the gas mass, it's dynamic. By subtracting the stellar mass to the dynamical mass, you can have an assessment of what's the amount of gas in it. But for this case, you need non-merging system with resolved kinematics, or at least marginally resolved kinematics. And in fact, with Alpine, we can do that because C2 is really bright, so we can measure the line width, and we can even have access to the size of emission. And for some system, we can even model the dynamics for some of the well-behaving one. So because of that, you can have access to the dynamical mass and get a dynamical estimate of the gas mass by subtracting the stellar mass to the dynamical mass. And you can compare with the C2 inferred mass with the recipe proposed by Zanella et al. To convert the C2 luminosity into a gas mass estimate, which of course I say it's a star formation tracer, but the gas mass is correlated with the star formation rate. So in the end, it's really an egg and chicken problem to know which first, but at least you can check the consistency of these estimates. And the good news is that it's kind of agree. It's not perfect, it's not a great relation, but at least you can see that the answer is in average rather compatible at 1 or 1.5 sigma level, which is a good indication that C2 is a decent tracer of the gas content of galaxy when you have nothing else. And here you can also look at something else, which is the gas fraction versus redshift. So it has already been observed with Herschel and also lots of CO sample with PDBI and then NOEMA, that the fraction of molecular gas increase with redshift, and galaxies at high redshift have a very high fraction of molecular gas. And what Alpine tend to confirm using both the object which have dynamical mass, so the one with the cross, and the one which are just C2 detected, is that these fractions tend to probably flatten after redshift 3 with a much weaker evolution, or maybe not evolution at all. So that means there seems to be a plateau at roughly 2/3 of a gas fraction. But we have to be careful. It's really the first time we do that. We use a tracer which is not perfect. So it needs to be confirmed in the future, but I think it could be interesting to continue to probe that, because if there is a flattening, it will be interesting also to try to explain it from a theoretical point of view. And finally, with C2, the last big stuff we can do with Alpine is to look at the luminosity function. So we can do it from the sample itself or from the serendipitous detection, and compare it with models which give us constraint about the evolution of C2 emitters, which is important for various types of model, to basically check if the amount of gas and the physics of the ISM is well done in these models. And typically you can look in blue in the field. So we look basically at frequencies with our setup, which are very far from the Alpine target, where we are kind of independent in terms of volume. And in pink, it's the field. So you also see the luminosity function is higher of C2 around the Alpine target, which highlight basically that there is indeed a lot of clustering at this redshift. But you look at the other stuff, you have a sort of volume-free measurement. So now I will discuss a bit of gas dynamics outflow and the C2 halos. So thanks to Alpine, we don't have very high resolution image, so it's not as impressive as when you look at lens sources or super bright objects, but at least you can have first indication about more normal behaving star forming system in the early universe with C2 spectroscopy. And C2 is very bright, it's an optically thin, rarely optically fixed, optically thin line. I didn't make a typo. So it's ideal to measure dynamics of icy dusty system, because H alpha is really hard to observe. Lyman alpha is not really probing the gas itself. It has very complex radiative transfer. So typically that's one of the best lines to study the dynamics of this system. And the first system we published in Jones et al. 2019 was a triple merger, which was booming even in a quick and dirty first quick look reduction of the Alpine data, where you have basically three components, so east, center, and west. each has a different velocity. And you can see on the position velocity diagram that they are really at different locations in the velocity diagram, which really say that there are 3 different components separated dynamically. And so Garrett discussed this system, estimate that it has already a large stellar mass, a lot of star formation, and that's typically the sort of thing you can highlight with Alpine very early. So then there was an attempt to classify more generally the properties of the Alpine sample. So there was an early classification which was visual based on the morphology, the dynamics, and ancillary data, with sort of quick look reduction made by Garrett using the same technique as for the first object. And then people classified by eye what they were thinking the system eye, and then there were disagreements, they discussed a lot, and it sort of converged until an agreement that there is a mix of rotator, merger, extended dispersion dominated system, compact dispersion dominated system, and also a couple of systems for which at some point it was not possible to say anything. So that was the first classification, which at least suggests, like, if you would expect that this galaxian domain sequence have all the same track in terms of morphology and dynamics, it's clearly not true. That there is a huge diversity in this system, and when you look at Alpine data, it's really obvious that there is clearly not only one track, and things are really not looking the same from one object to the other. So there is indeed a diversity. And Garrett is now preparing a paper where he's doing kinetic modeling for the brightest objects, which are also rather extended, so we can really resolve them with Alpine using the 3D Barolo code. Currently managed to classify 13 objects very robustly with like a quantitative criteria, not only by eye judgment. And he confirmed, even in this very bright object for which there is much less ambiguity on the classification, he still finds that there is a mix between rotators, merger, and dispersion dominated system. And here you have an example of a nice rotating system in the Alpine sample, where basically you see the object here. You see the very nice velocity gradient, highlighting the rotation. And then, of course, you made something more complex, look at the residuals to check if there's clumpiness or stuff like that, to see if it's really a rotator or if it looks like more a merger or something like that. But Garrett is preparing a paper with all the details about that. It's technical discussion, so I think we have to wait for that to have all the details. Then another thing we could do was to try to see if there was some outflows in this galaxy using basically the tails of C2, because C2 is expected also to be bright in the outflows. So if you have outflowing gas, you should see basically high velocity component of C2. It has been done a lot in the past with quasars to try to see the outflow, but we wanted to see if in a high star forming system, we could also see that. And that Michele Ginolfi did, he stacked all the Alpine C2 detection, sorted them in 2 bins, the most star forming one and the less star forming one. In the sample with the most star forming one, what he saw is basically that you have a tail at high velocity and low velocity, which could correspond basically to these outflows. So then he made a lot of tests also on how they behave spatially, the tail, and things are rather compatible with outflow. And there is a long discussion in the paper to highlight that's kind of compatible with what we could expect from a star formation driven outflow. Then there is another technique which allows to check for that. It's to look at the velocity offset between the C2 lines and other lines we detected in optical. Typically, C2 is really great for that. It's coming from the cold gas in the galaxy where stars are formed, so it's a very good tracer of the systemic velocity of your galaxy. Then if you look at other line like Lyman alpha, it's much more complicated, and it's linked basically to the gas around the galaxy. And finally, you have also UV absorption line, which comes from basically the outflows, which basically absorb the light between the galaxy and ourselves, and they are at different velocity. So with the comparison of these velocities, we can have access to a new type of information by basically having, for the first time, a rather cool and robust estimate of the systemic velocity. And that's what Paolo Casata did in this plot. Basically, it looked at the difference of velocity between the ISM line and the C2, and he found that for most objects, it's not that big. It's, in average, it's around 200 kilometers per second, which is compatible basically by slowly driven outflow with a bit faster system, but with nothing well above 500 kilometers per second, which is more compatible with star formation driven outflow, which is expected because our sample is selected to be non-AGN. So at some point, we don't expect too much AGN activities in this system. But after, there is a long discussion also with the set of Lyman alpha, but it's a bit more technical, so I invite you to refer to Paulo Casata discussion about that. Then we also look at the spatial distribution of the C2 around this ISFR system, both from an average point of view, that's the figure on the right, where you have basically the radius and you have the normalized flux. So in orange, you have the infrared continuum profile, which cuts really sharply around 1.5 arcsecond, which is roughly the extension of our system, which tells us basically there is not a lot of continuum emission beyond this line. For the low star formation rate system, it also tends to decrease kind of fast. But if you look at the more star forming system, you have a huge flattening up to roughly 3 arcseconds from the center, which can be interpreted as a sort of shallow halo of C2 around the core of these galaxies with a sort of core emission and then something more diffuse around. And in fact, some object can be identified individually. So CG Fundamental look at the size of the object and in fact found an excess of emission of C2 at large size compared to the continuum in 6 or 7 of the system. And when you look by eye, it's kind of obvious that there is an excess of emission of C2 all around this object, sort of diffuse halo of C2 around. So the current interpretation for that, but it's completely new, so it can be very debated. It's basically that if there is some outflowing gas, it may pollute the CGM, and we could have C2 emission from the TGM coming from the cat as some gas is sent basically around the system. But there might be over-explanation, and typically there are lots of projects of following up these sort of targets to understand in detail what is creating that. But that's probably an indication of the galaxies. These galaxies are not isolated system, and they have already early at this epoch an impact also on the metal enrichment of what's happening slightly around them. Finally, there is a really cool system which was found. Basically, it's a system with 2 detected optical galaxies. It has in situ 2 main blobs, but around there is this very hazy structure. So if you look more in detail in 3D decomposition, you can identify in the end 4 components for which you also have indication of optical flux. But if you model them properly, you say, okay, so that's already a complicated merging system. You take into account all these components, so it's basically in black, and you look at the total C2 emission of the system, it's much higher. So that means half of the flux of C2 in this system cannot really be explained by the compact sources that we have identified in this blob. So there are some attempts of proposal to try to observe it at higher resolution and deeper sensitivity to see if there could be satellites. But if there are satellites, they need to be super dust obscured because we don't see anything in optical, and optical go kind of deep. So if it's UV star formation, which makes this C2, in fact, it's not at all sufficient to explain this flux. So an explanation could be that some gas gets stripped out because of this merger of the core of these galaxies and basically is now floating around in the CGM. And it could be also an evidence, a bit similarly to the C2 halo, of potentially, let's be careful, a first enrichment of the CGM in complex merging system. But that needs to be confirmed in the future by future observation, but at least it's a first step. And this sort of things was kind of a surprise, and it was not even one of the science goals of Alpine, and that's typically something we found serendipitously. So if you want more detail about Alpine observations, there is now tons of paper online. So you have here the long list. And there will be much more detail and careful discussion about also the limits of Alpine observation, because of course from one continuum flux and one line, it's sometimes ambiguous to interpret it indeed. So then I will finish by 3 slides, a bit late, about other pet objects on which I love to work with, which are lens submitter galaxies. So Pierre is doing amazing work also with Alain now, so Alain is connected. with ZGAL, but I'm working with another team, the SPT SNG team. We have also studied this sort of system since a while. So typically the idea is instead of looking for normal objects, you want something very bright in order to look at more detailed feature. So one of the best way to do that is to say, okay, I have a super dusty galaxies at a redshift, which emit a lot at ALMA wavelengths. And if in between I have a big passive elliptical galaxies, it acts as the lens. It's almost invisible at ALMA wavelengths and it's transparent at ALMA wavelengths. So basically what you see with ALMA is only the arcs of the distant galaxy. And basically you can use optical images to constrain the characteristic of the lens. And with that, you get magnification for a factor of 5 to 20, which means you gain in integration time from a factor of 25 to 400, which give you access to fainter lines. And in the past, I looked at typically the dense gas tracer, which shows that the very star-forming system, we speak about 500,000 solar masses per year, tend to have a high dense gas fraction, which could also explain quick depletion time scale of the gas reservoir, indicating a very efficient star formation. And recently, Carlos de Bruck made a study with APEX, look at the oxygen and nitrogen line, and concludes that the ratio of lines of the far infrared line indicates that the systems are likely to have a metallicity between half and 2 times solar. So it's hard to give a better constraint because there's lots of uncertainty in this sort of modeling. But at least it shows that this system have an enrichment which is already similar to what we have in the local universe, which is kind of impressive. So it's not even the alpine system, it's even the monster, the top of the food chain at this epoch. And just to show quickly the work of Gayatri Gururajan, who is doing this PhD at LAM and on this SPT object. And she found really cool system and now can look at the dynamics of the system, so in a much more detailed way than Alpine. So here you have the integrated spectra, which is very weird blue shifted tail, both for the CO line in red and the C1 line in blue. And so it's kind of different line. Typically, CO is tracing the dense gas, where C1 is tracing the atomic gas. So it's sort of ratio between dense and atomic gas. And what the source looks like in continuum is this bright ring with here a sort of super bright gem, which is really strange. So initially we thought, oh, that might be an AGN, but why is it asymmetric? In fact, when we look at the spectra, we realize that you have here the center of the CO line, the C1 line, but you seem to have a sort of very high velocity component. And we imagine it's corresponding exactly to the blob. And then we did lensing modeling of this source. And what we found is it's compatible with a big extended disk and a very compact component, but which is not at all at the center, but which is more on the side of the galaxy. So we could think about a clump, but the clump would rotate at the same system, velocity as the system. So it's not likely to be that, but it may be a compact component, which is in fact independent. So either a satellite or a merging system. But it's still very preliminary, so it will request more analysis to confirm, but that shows when you start to use ALMA on these very bright sources, how much information you can get. And then we look at 3 objects in this pilot sample. So one is this object possible merger. Another one seems to be compatible with a rotating structure, and we are doing lens modeling to confirm that it's a rotator, lens rotator. Another one is compatible with very compact major merger. Here you see the PV diagram with the 2 components in the PV diagram. And then we can look what's the ISM properties at the various positions in this object. So here in the x-axis, you have the ratio between C1 and LIR, which is a proxy of the radiation field. Here you have the tracks of the radiation field. So the more you go on the left, the stronger the radiation field. And then you can look in y-axis the ratio between C1 and CO, which is linked to the density. And what we saw is here in green, you have a sample of IZ objects. The cross are basically low Z comparison sample. And in terms of density, it's not much higher, but what is clearly happening is we tend to have a stronger radiation field in this extreme system. Another thing that you can see in objects at 0103, you have a huge diversity of the radiation field across the object. So that's so the ISM in this system are really not at all homogeneous, and you have something very different in the compact blob and in the rest of the system. While for 2147, it's more compact and homogeneous. And for 2357, you have a core which is kind of homogeneous. And then you have a sort of external layer which seems to have a very high radiation field, probably in the outskirts of the system. So that shows basically that we are now entering the age where we can study basically the cold gas ISM property, even in a marginally resolved way for high redshift systems. So we'll probably learn a lot about that in the future. So to conclude, so Alpine confirms us that a significant fraction of the star formation up to redshift 6 was dust obscured. So there is still dust at already dust at redshift 6. So we have to be careful with that, and that shows that infrared astronomy has to continue to push to really see when we can stop to worry about dust. More systems are more obscured, so especially if you want to study massive galaxies, dust is important. The C2S relation is still valid at high redshift, which is kind of a good news empirically. We found large gas fraction in Alpine systems. So of course, one way to explain that they form lots of stars is the fact that they contain a lot of gas. It's not a big surprise, but it's a nice confirmation. Then we also confirmed through dynamics and morphology that there is a lot of diversity in the Alpine population. And one of the surprises was the fact that we could sort of highlight that there is some outflows and C2 halos around the systems, suggesting that the systems are not really isolated, and we already see first clues, I would say even first hints of a connection between the galaxies and what is happening around them. And then lens galaxies are more biased toward more extreme population, but they also allow to do a different type of science with a more detailed view on the dynamics and the ASM of IZ system, which are laboratory basically to study star formation in the most extreme large-scale environment. And if you're interested by Alpine, all the data products are aligned, the catalogs, the cubes, and the paper, of course. So if you're interested, don't hesitate to look at the public data release or contact us if this sample can be interesting for your science. The idea now is that as many people as possible use it to do their own science. That now the first analysis has been performed. So if you have any idea based on this, please contact us or download the data. We're really happy to help to do more science with that. Thank you for your attention.
Thank you very much, Mathieu. So now if you have questions, please raise your hand on the chat. Françoise, you can unmute and ask your question. Françoise?
J'entends rien. Ouais.
On t'entend pas, Françoise.
On t'entend toujours pas.
Son micro est ouvert, mais on l'entend pas. Ouais.
Ah mince.
Sinon, tu peux écrire la question dans le chat et je la poserai à ta place si tu veux. Okay, so meanwhile, Brigitte, do you want to ask a question?
On a un souci. On t'entend pas non plus, Brigitte.
Non, on t'entend pas non plus, Brigitte. Alors ça, c'est bizarre.
Tu as récupéré les questions dans le chat, Sandrine?
Non. Peut-être Hervé, hein, tu as une question, si tu veux essayer.
Oui.
Ah, on t'entend, merveilleux.
Peut-être qu'on m'entend. Voilà, bonjour à tous. Salut Mathieu.
Bonjour.
Well, it was a wide question. I was impressed, well, by everything, so that's super cool. Bravo. About your earlier plot on cosmic the Dickinson-Maddow plot, where you say redshift 5, everything will, well, at some point, everything should converge. Can you come? Go. Voilà, oui, celui-là ou l'autre, voilà. Ouais. So again, it's super impressive, but of course it's difficult. So there is a lot of scalar. Even when I was young in the field, people say, well, at some point there should be no dust at high redshift and so on. It seems that wherever we see, there is dust, and wherever we go, and your plot seems to show that wherever you go, dust is there, and this convergence between basically UV and infrared is kind of hope that will we see it eventually? And so can you comment on the fact that, of course, there is some scatter, and is there some guess or prediction on where it will actually happen in terms of redshift that dust plays a minor role? It seems that every time we push the limit back. Voilà, that was my question.
At redshift 3, it's a factor of 5 above. Now you see we are in the 1 sigma, and the uncertainty are not statistical. It's mostly systematics because we don't know the SED. So we put a lot of, like, the error bar are huge, but we were really careful with systematics, and we have been very generous on the error bars. Like we have been very conservative, but still you see at 1 sigma you're now compatible with half-half. And I played also game with some more empirical models, and there are some attempts in semiotical model to look at this. It seems like between 5 and 7, it should really happen. Like I can't imagine that it doesn't happen. After, the trick is the more you look at the most massive system, the more dust you have early. Just because you have lots of baryon early, so you can form a lot of stars very early. So I expect for the most massive system in the most massive halos, it may happen super early. But where, that's still an open question. And there is already this SPT 0311 sources I didn't discuss today, which is at redshift 6.9 and super dusty, super evolved. But maybe there is a monster even higher at redshift 8, 9. The question is, at some point it should stop. But we have to explore. And but yeah, my expectation is at 7, 8 that will start to be really hard to have dust. And statistically, I think at 6 it starts to be okay. At 7, except for massive system, we should be fine. At least it's half-half, so your beta correction becomes not too, even if you make a small correction of the beta slope correction, it should be fine. At least I hope. But on the other hand, like that redshift 6, it's the first exploration. There's a lot of work to really characterize what's happening in terms of dusty star formation. So it's like at least 10 to 20 years of work to do it properly, I would say.
Est-ce que Brigitte, t'arrives à parler? On réessaye ou pas? Non?
Ça ne marche pas.
Est-ce qu'il y avait d'autres questions? Any other questions? Don't be shy. I think people are more shy than usual when it comes to Zoom.
Ouais.
Brigitte, tu parles dans le vide, je pense. On te voit, mais attends. J'essaie. Ouvre ton micro. Ton micro est fermé, Brigitte.
Question en attendant.
Vas-y.
Vas-y, Henri.
Matthew, great talk. Sorry for asking the boring question at the end, but can you comment then on how precise are stellar mass estimates with only UV light? You know, this old question.
Only UV?
Yes.
We didn't.
Do you have any information about that now from the ALMA? Because I saw you're referencing that Hurricane. That's the UV only sample in HyperSuPrimeChem, isn't it?
So that was, I don't know.
That plot there.
Yeah, so for the stellar mass, basically, of course, we have this systematic. So what we did is we tried to use the same stellar mass estimates than the other people. Yep. So for this, we use photometry. So we have also IRAC. So it's not that bad, but of course, there are systematics. So when we do after the reconstruction, we try to be consistent in terms of the way to estimate stellar mass. So if there is a systematic for the SFRD, it should not be a problem. On the other hand, Alpine is not really helping a lot to get good stellar mass because currently we have only 1 point in the LIR, so you can use it to infer if your dust attenuation is not properly constrained, but it's not that easy. But there is in Marseille, Denis, Véronique, and students are starting to model this object with SIGAL using all the photometry from shorter wavelengths to try to see if it could help basically to correct dust attenuation and get better estimate of the stellar mass. But I'm not sure that's a good way to solve it.
Yeah.
It may be a bit better because your attenuation is better controlled, but yeah, I don't have an answer on that yet.
Okay, thanks.
But it won't be dramatically better. I don't expect. Brigitte,
Ok,
ça marche.
Brigitte, est-ce que tu as fixé ton problème de micro? Je crois pas. Non, non, toujours pas. Alors, juste, maybe I can read what Brigitte put in the chat earlier during your talk. There was 2 comments, very interesting talk, thanks. Luminosity C2, why not equivalent width?
So in fact, equivalent width in optical astronomy, it has a meaning because it's a continuum versus line. It's not as obvious in high astronomy because essentially the continuum at a given wavelength is not fully related to the physics of the emission of line because it's a fine structure line which emits through very different process. So basically, the relation between the continuum at a given wavelength and the flux of the line is not that interesting. So it's better to look at the line and look at the continuum value. So I think it's just coming from a slightly different physics. Technically, yeah, we could look at the line versus continuum ratio, but it's more interesting to look at the line emission versus the total infrared luminosity from 8,000 micron, because one is related to the bolometric energy emitted by dust, and the other is linked to the physics of one single line. So I think that's why we use that. I never really thought about that. I know we don't use equivalent width, but I think the origin of that is coming from the fact it's not as interesting as in optical because it links to less physics.
And there was another question, but I think you kind of answered that. So the other question from Brigitte was, is Alpine able to detect the outflows winds for ellipticals at high redshift above 4?
They are not ellipticals yet. There are some dispersion dominated systems which may be elliptical in the future, but currently we just show outflows in the global population. So we are not at the stage we can isolate proto-elliptical from other systems. But we see that there are outflows. And considering their stellar mass, we expect them to be passive rather soon in the future. So that's probably the outflows of what will be in the future elliptical galaxy, but there is still a huge extrapolation to do before going to that.
But you can separate in morphologies. You did this exercise of separating different types.
Yeah, the problem if we stack only the dispersion dominated, we don't have a sufficient signal to see something.
Okay.
So Alpine is big, but it's too small. So if you give me 300 hours of ALMA time, maybe we can try.
Okay, so are there any other questions? Doesn't seem so.
Françoise a réussi à poster.
Ben, je crois qu'elle a pas du tout. Je crois qu'elle a même quitté.
Ah.
Je ne sais pas ce qui s'est passé. Okay. I have a few questions, maybe to finish. So regarding the dust properties, you showed the infrared excess versus the UV slope, and you showed nicely that there are some points with interesting anomalies that are strange outliers. Can you give us a quick understanding of why are they so strange? Is it a problem of are there some anomalies in dust temperature, their composition, the composition of the dust in terms of silicates, carbon, whatever? Is there any understanding of that?
So there are many things which could happen. So first, there could be anomalous dust temperature. Because maybe it's lower metal enrichment or higher metal enrichment. So for some reason, or the dust geometry is different because the system has a weird history. So which could make a systematic, but I don't expect a factor 1.5 order of magnitude from just dust temperature. Other things could be also linked to heterogeneity of the system. If the UV, you could imagine an object for which you have a part which is kind of low dust emission, which emit lots of UV with rather blue spectrum. And then you have inside this object another region which is super dust obscured, which forms much more stars intrinsically, but which has very low UV escape fraction. So technically, you would see the small region which contributes few to the star formation rate, which is less dusty. So you would see a blue spectrum in UV, but you would miss basically a huge region which is dusty and more star forming. So basically, the UV slope is the UV slope of the flux you see, but the intrinsic flux could have a very different UV slope. So that could be an explanation. So there are studies, and Véronique Buaz started to look at these things, to look at resolved emission, is ALMA and UV emission similar spatially, if we could see something like that. Other things could be also the attenuation law could be kind of different. There are no discussion about much flatter attenuation law, which would change a lot of things for the system. So technically, yeah, there can be many things happening. But after we looked at it, and I don't think there is something obvious. The only answer we have is usually it's objects which are rather massive, which are IRX. So it's probably massive galaxies, which sort of reason appear rather blue. But the question is where this blue light comes from. Maybe it could even coming from regions which are not inside or accreted objects, or so. Still the question open. But on the other hand, I'm kind of sure that the system are actually forming a lot of stars. So it's something we'll have to deal with, and we need infrared data to do it properly for this sort of system.
Okay. Okay. Thank you for your answer. So just maybe a comment, remark, question. I don't know what it is exactly, but the problem with those high redshift galaxies that we kind of know that at least on theoretical grounds that those galaxies are expected to be extremely fluctuating in terms of star formation rate, much more than even intermediate redshift 1 galaxies. So to what extent the process of selecting those galaxies based on main sequence galaxies affect the result, and also that, you know, when you try to infer those properties from the properties of the galaxies as you observe it, are maybe just, you know, they are way out of their equilibrium state, because they are extremely stochastic. Again, they can vary in terms of orders of magnitude in SFR over a short amount of time. So
technically, they are main sequence, but it's a UV selection, UV magnitude selection. We don't select them to be on the main sequence. It's just if you select UV magnitude selection, you find very few starbursts. So that we don't exclude starbursts. But the second thing is, yeah, I think we have to take into account the time scale, because the time scale of UV star formation is not the same as the IR one. IR has a long memory, it's almost 100 megayear. So this redshift is non-negligible. But I think, Johan, we have to start to discuss the modeling of this thing. It's become urgent to think also about the theory. So let's discuss it later together.
Sure.
Okay, no more questions? Okay, if not, thank you very much, Mathieu. I'm going to leave the room session open for a while. If people want to interact informally with Mathieu, we can do that now. Thank you very much again.